Thank you so much for inviting me and giving me the opportunity to speak at this seminar. Right, so this is something which I could have done at once, but all right. So plan for this talk is to have a first 50 minutes where I want to talk specifically about the Farrell-Jones conjecture. So somehow try to give an idea of what the conjecture says. And the second hour, where I will try to present my work and also work of other people around this conjecture. So yeah, I hope this first hour is a bit more introductory. I want to start by recording a couple of instances of certain phenomenon. So you have some kind of statement you want to prove, either, as the title says, in algebra or topology. And then you have a statement involving K-theory, which implies the first one. So we will see, again, two instances of this, and this will suggest like general phenomenon, and the Farrell-Jones conjecture is somehow supposed to exactly fill in this picture. But I will somehow present two toy models first. So first one, so let me say this is first section of this first hour of talk. There is a conjecture called the Kaplansky conjecture. Can everybody read? Is it clear, more or less? Take a torsion-free group. And F a field of characteristic 0. Then 0 and 1 are the only idempotents in the group ring. So as surprising as it may seem, this is a conjecture. There is a way to try to prove this conjecture in certain cases, which involves the K0 group of the group ring. And yeah, K-theory of the group ring will be, I would say, our main subject of study in this couple of hours. Let me just recall something on the K0, but I guess everybody knows this. So let R be a ring, and some of the rings we will consider will not be commutative, namely a group ring in the case when the group is not commutative. So not necessarily a commutative ring, but with units. So the projective class group K0R, well, as you probably know, is defined as first you take the free abelian group generated by finitely generated projective R modules. So here, left, exactly, yes. So yeah, whenever the ring is not commutative, I will look at left modules. And then you mod out by short exact sequences. And then you have the reduced K0. So yeah, K0. So reduced K0 is, well, you can think of it as K0R mods free modules. Like more formal, if you want, this is a kernel of certain natural map you get from K0Z to K0Y. So why am I talking about this in respect to the Kaplansky conjecture? Because there is another conjecture. You have your torsion-free group. Then, well, first of all, reduce K0 of the group ring with integral coefficients vanishes. And for every field of characteristic 0, same happens for coefficients in F. Yes, so this is a conjecture. The point is that whenever you are able to prove this, this is also true. So proposition or theorem, let me say conjecture 2, let me say conjecture 1. Conjecture 2 implies conjecture 1. So whenever the conclusion of conjecture 2 is true, the conclusion of conjecture 1 is also true.
So let's say equals 0.
Oh, sorry. Yes. And there is another instance of this kind of principle, but for K1 instead of K0. So let's briefly also recall something about K1. Let R be, again, a ring. Then you can present K1 of R as, well, as the abelian group somehow defined by generators are, well, F conjugacy classes of automorphisms of a certain, well, of some finally generated projective left module of R module, and relations are given, well, composition is sum, and again, as above, you also want to mod out by short exit sequences. So F0 plus F2 is equal to F1 whenever there is, I hope everybody can see, but anyway, it's kind of the nature of, sorry, let me say P0, P1, P2. And then you have the same here. So this is F0, this is F1, and this is F2. And this is a short exact sequences of arrows. So everything commutes and the two horizontal lines are exact. Okay, you can think of this group in an alternative way, which is maybe more instructive. So there is a map, let me say remark, there is a map from GL of R, so all GLNs put together in a limit to this K1, inducing an isomorphism between the abelianization, so you quotient out by the commutator subgroup, and K1. In other words, you can find out that this commutator subgroups corresponds to the one spanned by elementary matrices. So, okay, anyway, K1 is some kind of quotient of GL. Good. The last remark I want to make about these KIs is that there exists a whole spectrum of K theory. I will talk more about that in the second hour. For the moment, let us just look at K0, K1, and know that there is a spectrum. Well, even non-connective K theory is a thing.
As for this conjecture,
Sure.
The K0 is 0 integrally, but not over the field. Like for F is a field.
Yeah.
This is not true if F is not a characteristic 0, right?
You mean there's counterexamples? I guess.
What's the significance?
I don't really know.
What does it mean about where those classes are coming from if they don't come from the sort of they're all part of?
Yeah, I don't know. Yeah, you mean what does this add? somehow to the.
Yeah, I mean, I guess that the first statement doesn't imply the second statement.
Sure, yeah. But I don't know, yeah, somehow the theoretic difference between this and this. Good. Oh, yes, and there's another abelian group you can build out of this A1 whenever you are assigned a group, which will be very useful for our topological conjectures. And that's the Whitehead group. So let G again be a group. Maybe I should say a word about our groups. Typically, I will look at torsion-free groups. There will be versions of what I will say also, which also makes sense for every discrete group. Maybe I'll make a comments about this. But in this first hour, I will only talk about discrete groups. There's going to be p-adic groups at some point, but yeah, main case will be discrete groups. And I will make a comment about why we're interested also in this second case. Yes, so consider the homomorphism from G times, let me say, Z2, a group with two elements, into K1 of Z of G, well, not into, actually. So which sends G, comma, plus minus 1 to multiplication by the 1-by-1 matrix here. So the class of this. In K1. The Whitehead group of G is defined as the cokernel of this map. So in other words, this is GL, and if you look at that characterization, this is GL of ZG mod everything. So mod G times plus minus 1 times elementary matrices. Of course, when I say mod, it's not like that's a subgroup, because, well, for instance, G may be not commutative. K1 is abelian, so I'm just saying I'm taking the cokernel of this map and also I'm quotienting that. Yeah. Okay. And now we get to topology. So just like in the case of the Kaplansky conjecture, I'm going to state a conjecture, and then I'm going to state a k-theoretic criterion for that conjecture to hold. Well, conjecture, well, sorry, some definitions before, of course. Let M be a topological n manifold for some dimension n. An H cobordism over M is an n+1 manifold with boundary W such that, so the boundary of W decomposes as one copy of M and something else, where this something else is also a manifold of dimension M. And the two inclusions of the two parts of the boundary, so M inside W and N inside W, are homotopy equivalencies. Both. So in particular, this is a way to exhibit a homotopy equivalence between M and N. It's one way. It's not like every homotopy equivalence arises this way, but it is one way. And we denote by H of M well, the set of H cobordisms over M, defined above, modulo homeomorphisms. Homeomorphisms rel M. So this means you have M inside W, have M inside W prime. You want this. This is a relationship, the relation you're quotienting about. Okay. Main theorem here is the following. If M is a closed manifold, closed means compact, no boundary, and the dimension is greater or equal than 5, then there is a bijection between this set of cobordisms and the wider group of the fundamental problem. So this already tells you that not every, I mean, this set doesn't describe the full homotopy type because it only depends on pi 1. However, I can anticipate that we will mainly look at manifolds which are aspherical. So somehow it makes sense that this suddenly describes a good portion of what's going on. Not everything, but a good portion of the homotopy type of M itself. Okay, and
is there a difference here between homeomorphism and diffeomorphism?
Good question. Not really in practice because you can do some, well, as it is, probably yes. But you're right that in what I'm going to say after, you can usually switch between the two in the sense that, yeah, I mean, you can rigidify kind of homeomorphisms you have to talk about diffeomorphisms. I think in general.
You haven't given any excuse.
No, of course, but
just replace topological placement. Usually this statement is stated in the.
What I want to stress. Yeah, exactly. What I want to stress is that what I'm going to say after is strictly topological. So the Borel conjecture, that's strictly topological. At this level, at the level of cobordism, so you have H cobordisms, S cobordisms, and those can be interchangeable in some cases. So in particular, in the proof of the Farrell-Jones conjecture, sorry, of the Borel conjecture, assuming the Farrell-Jones conjecture, which I'm going to explain later, this is the case. Yeah. But yeah. So corollary of, easy corollary of this, maybe I can also say it, but anyway, if weighted group of G is 0, then every cobordism is trivial. Every H cobordism over M is trivial whenever, so when, for every M such that pi 1 of M is isomorphic to G. Okay, and finally, as I just anticipated, I want to state the Borel conjecture, which is somehow the main underlying question in this talk. So first, me say what a topologically rigid, yes. Here, yes, totally. Thanks, yes. Not in what I'm about to say, but yes. Okay, so N closed topological manifold is going to be called topologically rigid. Well, I guess you expect what the definition is, but anyway. If for every map, from M to N, and this is another topological manifold, closed topological manifold, which is a homotopy equivalence. Homotopy equivalence. Then, well, if whenever F can is itself as a map homotopy equivalent to a homeomorphism. So in short, you can just say that whenever you have another closed topological manifold, which is homotopy equivalence to the original one, they are actually homeomorphic. This is a more precise statement if you want. So you can make that precise homotopy equivalence into a homeomorphism. Of course, the word closed here is important because otherwise you can just take S1, embed it into N plus. This is not a closed manifold. They are homotopy equivalent, but obviously not homeomorphic. Yes. Then let me also remind that a topological space X is called aspherical if, I hope everybody can see, pi I of X, well, connected topological space, pi I of X is 0 for every I different than 1. Let me also put I equal to 0, trivial, so connected topological space. So what does the conjecture say? Basically, according to the conjecture, if the conjecture is true, every aspherical manifold is topologically rigid. But let me state it in a more precise way. Borel conjecture for a group G. So let G be a torsion-free group. Which is, well, discrete, of course, finitely presented. Yeah, that's all actually. Torsion-free, finitely presented group. Then any closed aspherical manifolds, topological manifolds. I will never talk about smooth manifolds, but anyway, topological manifold M such that pi 1 of M is isomorphic to G is topologically rigid. So in other words, KG1 has only one representative up to homeomorphism, at least if you look at closed manifolds, of course. Yes. And finally, let me give you some state of the art for this conjecture. Well, it is true, proven, in dimension of M equal to 1 and 2. It is easy to reduce to check among the world of manifolds of the same dimension, of course. And once you do that, it's classification results. So that's not hard. It is also true in dimension 3, and it is a consequence of Perelman's work. More specifically of his proof of Thurston's geometrization conjecture. It is open in dimension 4, as for every statement I know in dimension 4, basically. And we will be interested in what happens in dimension 5. So it is also open, higher than 5. Higher, equal than 5. It is also open in general, but proven for very good class of groups. So let me say a broad class of groups G by means, so the way it has been proven, and the main names in the various papers around this high dimensional case are, well, first of all, Wolfgang Glück, then Arthur Bartels, Holger Reich, and other people, but definitely at least these three people. So via the Farrell-Jones conjecture, which, as I anticipated, is a statement about K-theory and L-theory. So again, we're going to see something formulated in K-theoretic terms, which implies something in topology. And somehow this is really a kind of generalization or expansion of the other, well, it's not on the, yeah, this kind of result here. I mean, it is literally related, but it's more powerful, of course. Yes. But as I just mentioned, in order to introduce this Farrell-Jones conjecture, we need to talk a bit about L-theory, because I didn't mention L-theory yet, and it's half of the conjecture, basically. So, but maybe it's also a good moment to stop for questions while I erase the second part. Okay, if there's no questions, let me proceed with some more definitions. So let me say, well, I skipped 1, 2, which was Borel conjecture. Let me say 1, 3. Hopefully some understandable basics on L-theory. Let R be a ring, and M a finitely generated projective left R module. A map, a morphism of abelian groups. Q from M to R is called a quadratic form. Well, you probably know this already, at least in the case of fields, but it's going to be the same thing. If, well, first thing, Q of AX is, well, A squared X, at least in the commutative case, sorry, QX. For every A in R, X in M. And well, I'm going to write the details of this because it's going to be very useful, I think, to understand what a quadratic structure on a stable category is. So let me just parse all the parts of the definition. So the symmetric form associated to Q by polarization, I guess it's called. So this form here, sending xy to Q of the sum minus Q of X minus Q of Y is bilinear. I mean, somehow it makes sense already that this form parameterizes a defect in kind of linearity of Q. So, but itself it's bilinear. So okay, Q is not linear, but the associated symmetric form is bilinear at least. And let me also say that the form Q is non-degenerate if this morphism here, well, let me call it BQ blank blank from M to, sorry, HOM and R over R, which sends M to beta Q M blank, is an isomorphism. So M is, well, the quadratic form induces a duality on them. Right. And finally, okay, maybe I don't want to write here because I don't know how much people will see. So let me maybe not erase the conjecture for the moment. So yeah, last thing I want to say. So in the non-degenerate case, Lagrangian or M and Q is a direct summand N inside M such that, well, this set here, which I'm going to define, so this is defined as those elements of M such that the symmetric form vanishes against M vanishes on all of N. So this is a definition. Content of the sentence is this is exactly the same as N. I mean, I don't think there's any obvious inclusion between the two, so it's literally a two-sided requirement. Okay, so for vector spaces, maybe it's a more familiar notion, but as you can see, it's verbatim the same for modules. And one thing we're going to consider is a variation of this, where R is supposed to have an involution. Like it's supposed to be equipped with an involution. So definition, let tau be an involution of R. In case R is not commutative, it's going to switch multiplication. Then, well, we have a similar notion of quadratic form. So Q of AX is going to be A QX tau of A, or the opposite. I never remember, but I think it's like this. Okay, let me just not rewrite everything. But the rest is the same. So finally, we can define what the zeroth L-theory group is. So it's going to be a group, an abelian group associated to the ring, and possibly to the involution. Let me just omit the involution for the moment. I will just make a remark after. So this is pairs MQ as above. So Q is going to be a quadratic form. Non-degenerate. So, well, non-degenerate modulo Lagrangians. And L0 R tau, if you have an involution prescribed, is well, the same thing, but now the notion of quadratic form also has to respect the involution. And there is a very important letter to add here, which is Q for quadratic. So it's not the same Q, but it means quadratic. And I say it's important because there's many flavors of L theory. So you could be looking at symmetric forms and you have a different notion, or you could be looking at actually many other flavors of L theory and you have a whole taxonomy of those. We will slightly touch another one later, but this is the main one we're interested in, quadratic L theory.
Is there an easy way to say what are the possible tables I can put inside of the Q?
The possible, sorry, what?
Like, what are the various forms?
Yes. Well, there is a hierarchy somehow. Quadratic L theory is on one side, symmetric L theory is on the other side. And when I say side, I mean that in between. So let me say LQ, LS. You have other flavors. And the way you construct those is by, well, I could tell it to you easily later when we do quadratic structures. But
correspond to like forms of SON or something like that?
Good question. I'm not sure. I'm not sure. Sorry?
When you get the different forms, but the L1, L2, L3, L1, L2, L2.
In that sense, yes. I mean, if you make n vary, yes. But yeah. But yeah, exactly. This is Tate's word. Yeah. Oh, and as I mentioned about K-theory, we also have a full L-theory quadratic L-theory spectrum. I will denote this. Yeah, so pi i's of that spectrum are going to be the abelian groups of 0, L1, and so on. I'm not going to say more about this. I need more about this, actually. Oh, and one last remark I want to, before presenting the Farrell-Jones conjecture, is that there is I mentioned involution for a specific reason. Which is the following. In the specific case where, well, say A is a ring, then consider, and sorry, G is a group, then RG has a natural involution, which is not the identity, sending G to G to the -1, oh, sorry, capital G, and leaving R fixed. Okay, so coefficients stay the same, but you invert the elements of the group. And we're going to use this. Okay, so I can finally state the Farrell-Jones conjecture.
I'm a bit disturbed by this modular function. So
I know.
W is if I have a metabolic
Yes.
and forcing n to be L plus L per.
Yes.
Yeah, and then. So what do you mean by modular?
Exactly. I mean, it's modular the existence.
One to it.
What?
If it exists, if it admits one.
Yes.
Then you kill it.
Yes.
Okay.
Yes. Yeah, I'm not going to talk about GW, but it's the common setting where you should put K-theory and
That's what I see by modular.
Yeah. I mean, as far as I remember,
so it's not just like random modular. It must be like n plus n per. It's like the same as n. Maybe it's exactly.
Yeah, let me think.
N per.
So what you want to say is M has to be recovered as sorry, maybe I should have added this. Yeah, not just N exists, but
N per times N maps to N per.
Yes.
Whenever you see that, you put it.
Yes. Sorry. Yeah. Thanks. Right. There's a piece missing, I would say, right? Because you need to be able to reconstruct.
How do you know that this exists?
Because of the non-degeneracy of the
Non-degeneracy.
That suffice. Okay, thanks. Thanks both. And just write Fj for them now on. So let G be finitely represented torsion-free group. Then for every regular ring, spoiler, we're only going to need R equal to Z. So this is a bit of overkill. And by the way, there's versions of this without this and without this, but I won't state them. With involution, no involution. The so-called assembly map, maps, I'm going to make a lot of comments about this, but let me just write them for the moment. So this is going to be the K-theoretic assembly map from the infinite suspension of BGs, mesh K-theory of R to K-theory of the group ring. This is one, and the other one is in L-theory. So infinite suspension of G's, mesh quadratic L-theory of R. And when I say quadratic L-theory, I mean tau is equal to the identity. Going to quadratic L-theory of the group ring with, let me call this involution tau minus. So this is where we need involutions. So these are equivalences, isomorphisms, as you prefer to call them. Well, let me say equivalences, I'm more used to it. Equivalences of spectra. So this is a conjecture. And now I want to spend some words about like what are these maps. But and in particular, I mean, the maps exist. The conjecture just says that they're equivalences. And if R is not regular, the idea is that nil terms appear. If you know what nil terms are, you know what I mean. Otherwise, it's not important. Yeah, and let me just say a couple of words about these, especially this map here, the K-theoretic one. Right, so how to motivate the existence of a map from here to here? Well, let's observe something. So basically, whenever you have, this is kind of homology theory. So you want to say in what sense this is close to be a homology theory. Let me be more precise. So remark, if R is a regular ring, this here regular is important because of what I was saying before about nil terms. Then you have two observations to make. One is called the fundamental theorem of K-theory. I think it's called like this. I don't know exactly why, but maybe Alan knows why. Good point. Okay. Kn of Rz decomposes as Kn of R plus Kn minus 1 of R.
That's the reason why. So anytime you know Kn
Mhm.
or big N,
Uh-huh.
you know smaller.
Oh, sure. Yeah.
Across all rings.
Yeah. For every N. Thanks. And the other observation is if G1 and G2 are, well, again, two torsion-free groups, finitely presented, then you can split the reduced K-theory of R of the free product as reduced K-theory of the first one, the first group ring, of course. Direct sum the other one. Yes, everything is reduced. Now, the observation, the reason why I'm saying all of this is that if you have any generalized homology theory, similar statement is true, meaning, so the other observation is if, let me say, H star is a generalized homology theory, then you can try to compute this. This is going to be two copies. Sorry, yeah, BZ, so the sphere, the S1. Two copies of the value at the point, well, shifted, of course, once shifted. So similar statements. And same for like, take the reduced version and you try to compute it at the classifying group space again, you get a similar splitting. So Hn reduced of BG1 plus Hn reduced of BG2. So what you're asking now is there any generalized homology theory such that if I put B of my group inside, I get exactly K-theory of the group ring? And that's exactly the kind of question that Joe's conjecture was asking. So maybe I can just finish. So I don't want to erase the conjecture. Just want to observe the last remark is that if H, let me denote it like HR star because it depends on R. if there exists a generalized homology theory such that H R star of G is K-theory of Rg. Well, in particular, by evaluating it at the point, then since we want HRn at the point to be equal to Kn of R, since it's a generalized homology theory, the only reasonable candidate is, well, the one we have there. So infinite suspension of your things mesh K sub. Yeah. Questions? Okay. So back to the Farrell-Jones conjecture. Two remarks. One remark and one theorem. So the remark is that if you play with this map here, and you assume that it's an equivalence, well, let me say, I don't know. Well, remark. Farrell-Jones implies, if true, implies the two results we mentioned before, so the two conjectures we mentioned before, so that K0 of the group ring with integral coefficients is 0, and this is easy from the conjecture. And if you make a couple of calculations, you can also see that it implies the statement about the weighted group. So weighted of G is also 0. It's fun because you get to, I don't know, I found it instructive.
We're there saying that if you knew there was a generalized homology theory, then you would prove the Farrell-Jones conjecture?
Yes, I mean, that's not exactly what I meant, but yes, I mean, what I wanted to say is the Farrell-Jones conjecture is asking this question, and the only possible answer is this, but we don't know if the answer is true. So yes, I mean, in some sense, that's what you're saying, yeah. I mean, it's trying to motivate why the conjecture is reasonable. So let me say, this is the only part, and this is the if part, meaning there is a reason to think that such a thing exists. And the last remark says, if it exists, it has to be like this. So, I mean, it makes sense to try to prove this kind of statement.
The reason for thinking it exists is because when G see it exists, that would be the same.
No, I mean, the two things together. I mean, this is the first thing, yes, which corresponds to, yeah, and the second thing corresponds to this. Yeah, there are two observations that lead to think. Yes. And the other two consequences I want to underline are the following. So one, maybe I can erase this. One is the promised one theorem. So this theorem is actually directly due to Farrell-Jones. And then it is, let me say, put in context with the proofs of Farrell-Jones by Bartels and Luke. Farrell-Jones implies Borel. Sorry, maybe I want to be more precise. Farrell-Jones for, well, G is free. I mean, can be any torsion-free finitely presented group. R equal to Z. So this thing here implies Borel for dimension greater or equal than 5. And this is proven. So Bartels and Luke and other people proved some instances of this, and they got this. Yes, so I just want to say a couple of words about why this implication works. But maybe before the pause, let me finish recording some state of the art and the other consequence. So state of the art for Farrell-Jones. It is, so there's basically two classes of results. Ones are positive results, like, so true for certain classes of groups. Let me just mention, I mean, the main one is this one, hyperbolic groups. And then you have and others. So finite dimensional cut zero groups, virtually solvable groups, yeah, a lot of like some mapping class groups of surfaces and so on. And the other thing I want to say, which is very important, is inheritance properties, meaning the class of groups for which is true, for which Farrell-Jones is true, is closed under subgroups over groups, so something containing over groups of finite index. And let me say, most importantly, from my perspective, directed colimits. Why is this important? Because apparently in geometric topology, a standard way to build counterexamples to such statements or to many statements is you find a suitable diagram of hyperbolic groups and take a directed colimit of those. And that's a very common way to build counterexamples. Well, here you can't, because it's true for hyperbolic groups and it's closed. So in particular, the conjecture is open. There's no known counterexamples. And yeah.
Give an example of some group for which it's not.
I thought about this. I don't remember if I found an example. No, I don't remember if I found an example. Yeah, sorry. But
Like someone who isn't.
no, definitely, yeah, definitely. The impression I got is that, I mean, I know nobody who's actively trying to prove it for new groups. So many people are very happy with this class, but there are counterexamples. This is what I know. I mean, it's not proven for all groups, discrete groups.
It's not the ideal formulation. It's the reason.
I mean,
you should write colimit across all virtually cyclic subgroups.
Exactly. So what I want to say is that if you remove this, there is also a version where the left-hand side is more complicated. Somehow makes more sense, let me say, but is more complicated. And that conjecture is proven for all these groups. If you're torsion-free, this is what you're proving, otherwise not. But yeah, very important remark, yes. It's not only about torsion-free groups, not at all. However, it's only for torsion-free groups that you get something related to Borel. Okay, I guess, I mean, I wanted to say another thing, but I'll just say it after the pause because it's 3 p.m. already. Good question. Well, of course, I don't remember off the top of my head. Maybe I wrote something here. No, I didn't. No, but that's definitely a good question. Maybe I can look up in the pause. I mean, one of these classes is these cut zero groups. So among those, there's, I mean, many things are proven in by geometric group theory, so it would make sense.
There's some coffee downstairs.
You know about the paper with no one on this? You put a billion and put R any ring.
Yes.
This is true during prismatic homomorphism. It's in his website.
Should I?
You get to.
Thanks. Okay, I just want to record one important thing for later. So another consequence of that. Yeah, so let me say analog of the fundamental theorem in K theory, but for L theory. This is the Shenson splitting theorem. And it says the following. Well, it's more than a remark, actually. But so if you take G equal to Z in Farrell-Jones, I mean, of course, this is an independent theorem. I just want to underline the relationship to the Farrell-Jones conjecture. Then you get that quadratic. Oh, did I write? So there I want quadratic. I think in Farrell-Jones. I mean, in the end, nice thing is that you have the what's it called, the Rothenberg sequence that relates some flavors of and the surgery exact sequence. So via that, but I think you as input you want quadratic. But yeah, I mean,
Because
Yeah.
LQ is like TC and LS is like K. Oh no, LQ is like K theory is like LS and LN is like TC.
mhm.
So I don't know then.
I mean, there's different flavors and some are closer to.
LQ is not the right analog of K.
So the thing you want is you want that to parameterize certain spaces of simple homotopes. So you want that to reduce to simple L theory. And I think quadratic is the one that gets closer to it. But I can double check.
It's because quadratic L theory is the one that shows up in the survey.
Yes, exactly, yes.
So are there other forms of Farrell-Jones conjecture or like the other forms of L theory?
I'm not sure Farrell-Jones is supposed to hold for others unless, I mean, they coincide or yeah. I mean, simple L theory is something that you use to prove Borel, but it's not standard flavor of L theory you're interested in. Yeah, I don't know.
So quadratic L theory is not special among these various forms of L theory.
Not really. I mean, as you mentioned, is that it's used to relate it to.
Very special.
I mean, but also symmetrical theories. I mean, the others are less special, of course. But
Okay,
yeah, the extremes.
Is this conjecture also supposed to be true for symmetric L theory?
That's what he asked. I'm not sure. I should double check. Yeah.
If you knew for both of those, would it imply for the other ones in the middle too? No.
I don't think so. Yeah. Yeah. So this. So if you take the ring of Laurent polynomials with the involution I mentioned before, the one which sends x to the minus 1, is also decomposes. And there is an analogy, let me not write it, but there is also, this is going to be important, however, there's let me say generalization of this result for twisted Laurent polynomials. So basically, it describes quadratic L theory of this ring, where alpha is an automorphism of R. And this is the same underlying abelian group, but multiplication is twisted by this automorphism. And you don't get a splitting, you get an exact sequence, so it's weaker. I will come back to this kind of thing because it's corollary of a result of mine and other people. But I wanted to mention this because it's a direct generalization of this Shenison splitting. It doesn't follow from here unless you play with, you do something else here and you put the twist here. Okay. From now on, I will assume as background the theory of stable infinity categories and presentable stable infinity categories. Okay, maybe I should erase here.
You want this board moves?
Yes, I was wondering. Thanks. So let me just make some recollections. Feel free to stop for questions. I just do not intend to spend any time on this, but I want to recall that there is this paper by Bloomberg, Gepner, and Taboada. And after that, there's been many reworkings of this, but this somehow pioneering work. So there exists a functor from the category of small, stable infinity categories with exact functors to spectra, parameterizing a non-connective K theory. So such that K theory, like this functor evaluated that perf of a ring is non-connective algebraic K theory of R. Maybe one remark I want to make is that this kind of result is definitely not true for triangulated categories. So sometimes you, when you try to assume knowledge of stable infinity categories without assuming knowledge of stable infinity categories, you say, maybe you can try to think of those as DG categories or even triangulated category. Okay, this is one instance where it's definitely not true. Why?
Don't have to apologize for using stable infinity categories.
Ah, sorry. To you especially, I guess. DG categories is fine, and unless you want to play with the sphere spectrum, which I will at some point, but yeah. Yeah, so Niemann observed that there cannot be such a functor out of triangulated categories because cones in a triangulated category are not functorial. And moreover, like this functor has a very important universal property, which we'll not need. There are several motivations for such a setup, including IHÉS and many things. Let me just observe one thing, which I learned from, let me advertise this, 2023 IHÉS school on algebraic K theory. I'm going to steal from here for continuous K theory. So there's this lectures by Dustin Clausen. If you want to hear a clearer version of what I'm about to say in a moment. And also there was a talk by Thomas Nikolaus, which basically coincides with the, I mean, it's a large version and a clear version of the last part of the stuff. But what I want to observe, and I learned this here, is that one kind of advantage of this is that some constructions at the level of K-theory can be exhibited as you have a functor of categories, you apply K-theory to the functor, you get your original construction. For instance, if you have X and Y, two quasi-projective smooth varieties. Well, first thing, K-theory can also be defined for schemes. Comes in two flavors. One is K-theory of vector bundles, one is K-theory of perfect complexes. And one reason why K-theory of perfect complexes works better is that if you have a proper map here, there is kind of push forward in K-theory. But if you look at K-theory of vector bundles, you have to build it by hand. So you push forward your vector bundle, you get a complex, you have to resolve the terms, and then you find out that you do have a class in KY. But at the level of, if you look at K-theory of perfect complexes, then this coincides with K of push forwards of perfect complexes. And when I say it comes in two flavors, I mean that for some class of schemes, including fine schemes, they're the same, but not for all schemes. So somehow a choice, and there's reasons to look at K-theory of perfect complexes, which is what we're going to do. And this idea that some constructions which were somehow more by hand become just apply K-theory to something is literally what I want to talk about at a different level. The other recollection I want to make is, unsurprisingly, about L theory, like similar kind of setup, but for L theory. Yeah, I don't have time to recall what, or to introduce what a Poincare category is. So let me just recall or mention that there exists an infinity category called cat P, which informally is a category of, well, the datum of stable infinity categories equipped with what is called a quadratic form, C to spectra. And for instance, something belonging here is curve R for a ring R, and then something called quadratic Q of R, which very roughly speaking parameterizes quadratic forms. So kappa Q of M belongs here, is quadratic forms. So this doesn't, of course, make sense because this is just a set. It's not a spectrum. Somehow a connected cover of the spectrum that you're looking at as a space parameterizes, vaguely speaking, that. Unfortunately, I don't have time to be more precise about it, but idea is you can vary, like you can change this as much as you want. And so it's a very good tool to encode all other forms of L theory, for instance, that you want. And why do I say, like, what does this have to do with L theory? The result, an analog to that somehow, sorry, theorem. And this is in the, let me write this. So this is the second paper of the series called, informally, I guess, the 9 authors papers. I don't have time to recall what the 9 authors are, but you can ask me about the title. So the title of the series of paper is Hermitian K-theory of stable infinity categories. So here they prove that there exists a functor from cut P to spectra such that, for instance, sorry, let me call this L. L of curve R. This is pronounced kappa, it's a Phoenician Q, is quadratic L theory of R. You can also put the involution in it. There is such a thing as this, and you can put involution here and you recover that. But really, I mean, you can put many other variants here and you get other flavors of L theory. You get also stuff which is not L theory. There's a more general functor, as Ellen was mentioning, called GW. So
What is the connected?
This is the connected part.
I mean, this L is the connected version.
It depends how you define it,
So
but yes.
Form.
But can't you do this for non-connected as well?
I mean, the result will be non-connected officially, but it's more analogous.
I see. I see.
Okay.
Okay. So I'm going to say connective L theory.
Can you say something about, so there's 9 author papers and like there's several of them and they're very long. What's the like work that they're doing in these papers?
Well, I know part of the answer, of course. I think big part of the answer is GW, in the sense that cut P is the environment out of which you can draw an analogous functor called GW. Now, GW is Grothendieck bit invariance. And for instance, there is an exact sequence. Let me very simply write it like this. Of course, I should explain a lot of things, but GW is a big thing out of which you can not just recover, but put into context K theory and L theory. Of course, I should be precise about what variants I'm looking at. And so Poincare categories were a thing already in Loury's lectures in algebraic L theory and surgery, but they hadn't been used for this as far as I know. So I think this is the first foundational thing that they do. And once they have this, well, for instance, they can well, not redefine, but they can see L theory in this context. And ultimately, they define this notion of Poincare motives, which, well, it's motives, but in the Poincare setting, so it's something living under this. What I will somehow touch in the last part of this talk is that thanks to the existence of this functor, and well, of this one is, of course, but that's not part of the 9 authors papers, you can categorify the assembly maps, meaning similar thing as here. So there will be a functor of infinity categories. If you apply K theory, you get the assembly map in K theory. There's going to be a functor of Poincare categories such that if you apply L theory, meaning this functor here, you have a map of spectrum, that's the assembly map in quadratic L theory. So this second part especially is only possible if you have such a functor. And yeah, but let me say that what I mentioned is small part of the second one. Some foundations are in the first one. And the thing I said about categorification, well, somehow a baby version of it is in the fourth. In the fourth paper, which is in my email conversation with Jonathan, but not online.
But why are these papers so long?
So yeah, I should say 2 things, but let me only say one. They redo a lot of stuff in there. So yeah, I mean, some things could be just referred to, but then they wouldn't fit in the format, so they had to redo them. Especially this one was a nightmare as far as I understand, because there were conflicting versions of how to write things between the authors. So, okay. All right. Okay, I will now give a meaning to what I sketched now, like this categorifications results. And And then I will ask you to choose if you want assembly maps for Heike algebras or continuous K theory. Let's see how much time will be left. Okay, so let me say proposition. Let R be a ring and G, let me say a ring with involution. And G, again, a group, let's say torsion free. It's not really important here. Consider the constant functors. Let me call this Fk from the infinity groupoid associated to the classifying space of G to cut X, just sending everything to the category of perfect complexes. So also the level of every G goes to the identity. And another one, Fl, from Vg to cut P instead, also constant, sending everything to perf R kappa Q R tau. Sorry if I didn't have time to define this, but I can after the talk if you want. And also G to the identity. Yes. Then the colimit in this category, infinity category, of the functor Fk is equivalent as a category to perfect complexes of the group ring. Oh, sorry, I write it here usually, RG. And, well, the limit of Fl is almost the same as what you would like. So tau minus is the involution here. This is only true up to idempotent completion, just to be precise. Main point of this is that, moreover, so by the way, why is this important? Because this and this, if you take K theory of this and L theory of this, you get the right-hand side of the assembly map. So K theory of this is K theory, algebraic K theory of this. L theory of this is, well, one flavor of L theory of the group ring with that involution. And more is true, the full assembly map is recovered as follows. So you have a colimit exchange map. Well, let me say composition, right? So this is a functor to cut X. You can compose with K theory. So composition of this colimit has a natural map to K theory of the colimit itself. And same is and the colimit itself is this one. And the same is true for L theory. FL also has a formal colimit exchange map to L theory applied to the colimit. Now, as I just mentioned, by the first part of the theorem, this is K theory of RG. And this is L theory of RG, tau minus up to decorations. Good. And the content of this, moreover, is that this is the assembly map for K, and this is the assembly map for L. So in particular, also the left-hand sides give you back the left-hand sides of assembly, which is not obvious here, but well, I mean, it is if you do some computations. It's not obvious, actually, because you have to use some stuff.
It is very special with VG, like
No. You can put X, you can put a homotopy type, yes. But of course, in that case, you have to define what you put here, but totally, yes.
Sorry, why is it not obvious what the left-hand side is? I mean, it's just a constant functor. So it's a colimit of a constant functor, so it's always smashing.
Yes, sorry. No, maybe what I wanted to. Okay, yes, sorry. In the torsion-free case, it's obvious. Yes, it's what you get. Sorry, yeah. The non-torsion-free case, you have to compare it with something more complicated. Yeah, thanks. Here? Sorry, here. L. Above. Idempotent completion. Sorry. Yes. Yes. Meaning I idempotent complete the category. It doesn't have to do with the part. I get something whose idempotent completion is per. Oh.
Why did you need to do that there, but not for F?
Yeah, good question. I think just because, no, sorry, I think just because so maybe it's not that I only need it there, it's just that K theory doesn't see the difference, while L theory does. Yeah.
Yes, because you didn't use it in a formula.
Exactly. Yes. So yeah, I guess in principle, I should put it here as well. But K theory doesn't see the difference, L theory does. Yeah, thank you so much. But there is a version of L theory which is just forced to be Karoubi invariant, and okay, with that you can remove it, but of course. But it's not just an artificial thing, meaning that in good cases you recover, how's it called, like minus infinity L theory. I think it has a name, but I don't remember. Okay, so let me just say now that I want to write it here. Let me leave these two lines. Or maybe I can also move the board. But anyway, so goal of many people exhibit assembly of K and assembly of L as K applied to some functor and L applies to some functor. So here you see that the right-hand side is L theory evaluated at some category. This is not true here. This is a colimit exchange map, so L theory is inside. I will talk about an answer for this, for the L theoretic case, which is my work. And then in the last remaining minutes, I will say what is being done for K theory. So, theorem. In myself and Sonia. Let I be a small category and F a diagram from I in, okay, this is a new thing. It's cut H is a pre-cut P. So it admits, it's a super category of cut P. Cut P is something inside here. To be formal, I have to say cut H, and I can make a comment about it, but maybe after the talk. Then there exists something called Hermitian, okay, let me just say it where it works, Hermitian unstraightening of this functor, which will consist, like pretend it's something here, so it will consist in some stable category and some quadratic structure. So this belongs here. With the universal property that functors out of it inside any other Hermitian category are the same as sections of the Cartesian unstraight. So this is going to be Hermitian functors. I never explained what it means, but it's like morphisms in this category. Sections of the Cartesian unstraightening of the functor, Hermitian functors from F blank to C. 1, 2, 3, 4. Okay. This is the universal property. In other words, this functor here admits an Oplaks colimit in this category. And the comment I wanted to make is that there's no such things here. So Oplaks colimits only exists here in the sense that this is a reasonable 2 category and this is not. There's very nice reasons why that is not, but yeah, don't have time. Sorry, yeah, it's very messed up, but fun II means, so this is something, some vibration living over I, and this is sections.
In sections or Cartesian sections?
Sections. I mean, this is no, sections, yes. Yeah. Okay. So these are very theoretical results, but it allows you to say the following. Okay, let me say this theorem again. Let G be a finitely presented group K is not K theory here, sorry, K is a simplicial complex such that its geometric realization is the classifying space of G. Let I be the opposite of the category of faces of K. And finally, let F as there, so from BG to cut P be any functor. So maybe I should make a picture. So this thing being the category of faces, well, its opposite, admits a localization to BG. So BG is the underlying groupoid of I. I mean, it's not totally obvious from the definition, but it is true. So it's not just this is the definition. If this is true, this is also true. Like, this is also true. And then you have a functor from here to cut P. So in particular, you have a composition. Then this thing, so this is a localization in the sense that it exhibits BG as not the underlying, sorry, the enveloping groupoid of I, induces what is called, let me just write it, Poincaré-Verdier projection. So it's basically a quotient of stable categories. Phi from UNH of F lambda. So F lambda is this composition here, and UNH is this Oplaks colimit thingy that exists in the Hermitian setting to UNH of F. So this is F lambda and this is F. Two different things. Now this is the colimit of F. So it's not an Oplaks colimit because basically because it's groupoid. It's not just a category, it's a category where everything is invertible. And so this is a priori an Oplaks colimit. It's actually a a strict colimit. This is not.
It's a localization.
Sorry?
This is a localization.
This is also localization, yes. Yes, this is also localization. It's actually Poincaré-Verdier projection is in particular it's a localization. In particular, this is going to be very technical, but part of this means a non-obvious thing. The kernel is Poincaré, whatever this means, but it's very important. Okay, and finally, So in our work, we give some description of this kernel. Why? Because, well, this is, again, the right-hand side of the assembly map. You would like very much for this to be something whose L theory is the left-hand side of the assembly map, which is the case, but you have to prove it. So a good thing to know would be, well, where does the kernel of this localization go under L theory? It doesn't go to 0 in general, but the fact that it's Poincaré basically gives you the elements to prove that the L theory of this is the left-hand side of the assembly map. Let me just write what I just said. Proposition, or corollary if you want. So if R is a ring with involution as usual, and F is the functor FL I defined there. So the constant functor with value perf R kappa R. Then L theory evaluated at phi is the assembly map in L theory. In particular, the left-hand side coincides, which is, again, not obvious. And we gave an application of this to reprove basically the Shenison splitting theorem, or more precisely, its twisted variant. Because thanks to this description of the kernel that I mentioned, there are some cases where it's easy to prove that not only the kernel is Poincaré, but it's what is called hyperbolic, metabolic, but even hyperbolic. So the L theory of it vanishes. So, well, yeah. Corollary. Let me synthesize it like this. Recover the following long exact sequence, whatever this means. This is the thing I mentioned, which is also Karoubi invariant. It's a kind of generalized splitting result for Laurent polynomials twisted by L theory of Laurent polynomials twisted by some automorphism, and so on. So there's a long exact sequence of L theory groups relating, we're never going to read this, but relating L theory of the twisted Laurent polynomials with tau minus. Oh, well, here, let me just simplify it. Not put tau, but have tau minus there. And shifts, possibly shifts of L theory of the ring itself. In particular, if alpha is not twisted, if alpha is the identity, you recover, I mean, the sequence splits and so on and so on. So what we did is just we recovered this result, which was due to Ranitsky. Even in the twist case, this was Ranitsky's work with this technology. So we were actually able to prove that you can construct a Lagrangian in the infinity categorical sense for this kernel. Okay, so, okay, fine. I just wanted to say a couple of words about what you can do for K-theory. Because this is what I would call a categorification of the assembly mapping in L theory. So let me repeat it again. You find something whose L theory is the left-hand side, and you hope that this will help you in proving that this is an equivalence. Okay, by looking at the kernel of the functor. Something I didn't mention is that L theory sends, let me say, exact sequence of Poincaré categories to exact sequences of spectra. So whenever you have that the kernel goes to 0, then the map here is an equivalence. There is ongoing work to do the same for K-theory. But it turns out that for K-theory, it's not as simple, provided this is simple, but you can still do it up to working with this continuous K-theory.
So co-assembly is simple.
What's co-assembly for you? The map in the other direction.
Because there's local systems against sheaves.
Yes. Yeah, sure. Yes. I mean,
Pretty obvious.
this is a very important interpretation. You can exactly what you try to do in some sense is to realize the assembly as kind of you have a constructible sheaf, you put together all your data and you get a local system. And yeah, that's basically Lurie's input. Yeah. And one reason why all this works for L theory is that L theory is Bordism invariant, so it's somehow homotopy invariant in a certain sense, which K theory is definitely not. So, yeah.
L theory behaves more like K0.
Yeah, if you want, yeah. Yeah. Jonathan says that L theory is simpler than K theory. I mean, easier than K theory. Some people had to object, but yeah.
Because you can interpret every Ln plus for any n as like an explicit complex. It really behaves like K0. Like you can make arguments like pointless. Well, I have that. It's not so good. And it's also like periodic.
Yeah, it's more periodic. Yeah. What did I want to say? Oh, well, yeah, let me just state it. Again, if you want to learn more, there's plenty of sources. I personally recommend Dustin's lectures for this 2023 school. So in short, continuous K theory is a functor from what are called dualizable presentable stable categories to spectra. And the point is that this contains, let me say contains, it's not a full subcategory, it's a faithful functor. No, it is actually, no, okay, because you require them to be strongly continuous, so no, it is. The thing out of which you had already K theory. I don't have time to explain why it's very useful to extend it, but one instance is exactly this. So there exists a category called Cauchy's hats of BG with coefficients in whatever thing you want. I mean, spectrum implies everything, which belongs to this, but not to this. It doesn't belong here. I mean, in the sense of this inclusion. So it's not compactly generated. This is the thing that you should say. And plus a map, functor, from this Cauchy's hat to maps from, sorry, from BG to spectra, such that continuous K theory of this functor, let me call it phi, is the assembly map. Okay, this is a super synthetic version. And this is work in progress by Bartels, Efimov, and Nichols. So they have this kind of results. And what I don't have time to talk about is the assembly map for KK algebras. So if you're interested, I'm here. And that's all. Oh, maybe I should also say that this was introduced by Sasha.
Questions?
Honestly, the G is please.
No, I don't think so. I don't think we use this anywhere. No. No. I mean, I can double check, but I don't remember using this. The intorsion free is usually something that, yeah, okay, depends what you want to check. No, of course. Yeah, it depends what you want to check. No, but it is true. No, it is true. So what you prove is that it coincides with assembly map in the sense that it coincides with the colimit exchange map. And then separately, this is not our work. You can always prove that the colimit exchange map coincides with assembly, even in a not every case. But yeah, that's also an alternative definition of the assembly map. But
Can you say what the hat means? Does it mean paper completion?
no. I think hat means in the large setting, meaning that this is a dual of a category of sheaves. So this is something I can say. So you have sheaves, honest sheaves of like for any topological space. Let me say locally compact Hausdorff. And let me also say compact Hausdorff because duality statements work when X is compact with efficiency spectra. So this again lives here, doesn't live here in general.
Hat is just pure notation.
Yes. So Cauchy's hat is this thing dual in the Lurie tensor structure here. And then, as we mentioned with Nick before the talk, it's very hard to say what category this is. But it's compact objects, I mean, for obvious reasons, are understandable, and all other objects are not. But yeah, it's the dual.
Does it help to understand its compact object? I mean,
It does.
Compactly general. Right?
It's not, but there is one compact object which it's called, I mean, Nicholas called it high log. It's a certain thing here whose class in continuous K-theory is a lift of a certain element on the right-hand side, and this is something related to Wall's obstruction, if I remember correctly. It's called a simple lift of a certain class. Which
Not like a constant.
Because your space was.
Yes.
Which is not true for sheets.
Yes.
This roughly is the thing corresponding to the constant.
By the way, there is a theorem by Efimov saying that continuous K-theory of this is cohomology with coefficients in K of R when this is mod R or K of the sphere spectrum. So this is somehow apply duality, get homology in some sense, for instance. Thank you.